Hello everyone. Today I am going to discuss or explain the use of the multisim along with the VHDL code or to write the VHDL code for different digital design. So to start with, I am taking the example of the header to explain how it can be done in the multisim as well as how we can write the code VHDL for V for basic, VHSIC very high speed integrated circuit, HDL for hardware description language. So we'll try to write the VHDL code for different digital design. Also we'll do it in multisim. Okay, to start with, we'll start with this binary header. Now all of us we know what is the binary header. It's follows 0 plus 0 is equal to 0 which carry 0, 0 plus 1 is equal to 1 which carry 0, 1 plus 0 is 1 which carry 0, 1 plus 1 is 0 which carry 1. That is the binary addition. Now while talking about the binary header, always we start with the half header. Okay, so half header is nothing but a logic circuit in which there are two inputs only, A and B single bit, and there are two outputs, sum and carry. Now as a part of the digital design, particularly the combinational design, the first step is to understand the logic statement. Here the logic statement is to design a half adder, single bit half adder. The next step is the truth table. So as I have mentioned in the binary addition, so accordingly it follows the truth table for the half adder. This is the truth table for the half adder. So here since there are two inputs, there are four input combinations 0 0 0 1 1 0 and 1 1, and accordingly if it is 0 0, 0 plus 0 is 0 which carry 0, 0 plus 1 is 1 which carry 0, 1 plus 0 is 1 which carry 0, 1 plus 1 is 0 which carry 1. After the truth table, next step is to get the logic expression in either SOP form, sum of product form, that is AND or inverter forms, or POS form, that is product of sum forms. Then we follow the K-map or Queenie-McCloskey law to minimize further minimization of the SOP or POS logical Boolean expression. Further, if you need further minimization, then we can go for XOR. Now in this truth table, hope you need not to draw the K-map because there are 4 minterms only, and for the sum there are 2 minterms where the output is 1, that is A bar B and A B bar, and that cannot be mapped in K-map. So therefore the sum output is A bar B or A B bar, and A, that is A bar B or A B bar, which is nothing but A XOR B. So in terms of SOP, this is the minimized expression. So as I mentioned, if you need further minimization, you have to use the XOR. So in XOR, finally it is 2 input XOR gate. Similarly in the carry, if you see, there is only one minterm where the output is 1, so it is AB. So there is no questions of minimization. So carry output, the logic expression is AB. Okay, so finally for the half header, the sum output is A XOR B and carry output is A and B. Okay. Now let us see how it can be designed in multisim. So this is your multisim. Here I am going to design that half header, that is your A XOR B, sum is A XOR B and carry is A and B. So we need 2 gates. So as you see in the multisim, this is a shortcut maneuver where you can directly get the library. So here we'll follow the TTL. There are MOS logic as well, but in case of bipolar logic, as you know, in the case of bipolar logic, the TTL is most widely used logic. So this is your TTL. You click on this TTL, so it actually open up a window wizard where the entire database is there. So from where this you can select actually it is master database, corporate database, user database. So we are considering master database, and in that master database there are further groups. Like right now, as I have clicked on the TTL, so it is showing the TTL only, and these are the different groups. Okay, and under the TTL these are the different ICs or the gates available. So here I need an XOR gate, okay, and an AND gate. So XOR gate, as you know, the IC TTL IC 7486 7486. So 7486 is an XOR gate. So as you type here component IC number, if you know the IC number, otherwise you can search it. So I know, suppose the XOR gate IC number, which is TTL IC number, which is 7486. Once you type here in the component, it will show you here. Now as many as you need, you can select from here. Okay, and you can see the detail of this gate. This is a quad 2 input XOR gate. That means it is this IC. Inside the 7486 IC there are 4 different similar gate 7486, which follows the TTL logic, and you can detail a code view model and everything you can see. Or simply you can click on this OK. Once you click on the OK, you see this ABCD is showing here. That the numbers different as many as you want. So I'm clicking on A, and here wherever you would like to place, you just click on. Suppose I would like to place it here, I just click on here, and I need only one XOR gate, so let us make it cancel. So once it cancel, then automatically this wizard comes up again. Next I need one AND gate. So AND gate, as I know, 7410 7408 7408 7408. There are 2 versions, J and L. Anyone you can take. So let us take 7408, and this is a 2 input AND gate. So just place say A here, somewhere here. Okay, cancel. Now this is your sum output, this will be carry output, and we need 2 digital sources for providing binary input. So there again, you click any one of these. Suppose I'm clicking on here to get the wizard, and now see this is sources. So in that sources, different types of sources are there, but I need the digital source. So just click on this digital source. So in the digital source, 3 different components are there: digital clock, or digital constant, forever constant, either 0 or 1, or interactive digital constant. So I need this where you can change 0 and 1. So let us suppose this is my A. Okay, I'm just closing it. You can change the level here. This is IC number A, IC B, U2A. So here I am you just double click the display and the level. Here it is showing U3. Suppose I am putting it as A. Okay, this is your A. Now just place the cursor on this. You'll see this, which is for connecting. So just click on it and drag it. Okay, once you see this red button, that means it get connected. Just click on it. So this red line means from here to here it get connected. Similarly, for this also I need the same A. So you just put it here. Okay, connected. Then similar digital source, I need one more. So just copy and paste the same again. Somewhere here suppose. And I just put it, suppose B, level B. Okay, then you connect it here. That is your B. Then this is also B, so you can connect it here, B. Okay, so this is your half header. Now to see the results for the sum and carry, what you can do is you can use some display device. So source, you just click here, indicator. This indicator, there are different types of indicators. Different types of indicators have voltmeter, emitter, probe, buzzer, lamp, virtual lamp, hex display, and all. So for digital display we can use LED also, or better we use some probe of different color. So these are the different colored probe. It is good for digital display. So here we'll use a blue display for the sum. You just put it here. Once you see the red dot, that means it get connected. Another one is for carry, I'll use some red dot. Suppose this is a red display. That's all. Okay. Now, since now just save it. I'm just saving it in a folder. Let me save it in the app drive. I'm saving it in I'm putting it as a folder. Same as this BSD data system. Okay, here I'm saving as design. Or say HalfAdder. Let's save it. So it's saved. Now this is your run button or F5. Once you click on the run, this circuit will run. Now you see currently the input is 1 1. So according to the truth table, when it is 1 1, sum is 0, carry is 1. So your sum is 0, carry is 1. Then suppose I am making both 0. So you see both the lights are off, display are off. That means sum 0, carry 0. Then say 0 1. 0 1 will give sum 1, carry 0. So sum 1, carry 0. Then say 1 0. Then again sum 1, carry 0. Then 1 1. Sum 0, carry 1. So that means it verifies the truth table. That's all. So this is the finally your circuit. I'm just copying it and I'll press it here. Putting it here. Okay, let it be closed first. Yes. Done. Okay. Yes, I want this part. I'll use some output here and create the output. So This is your finally the circuit. HalfAdder circuit. Okay. Now I'll show you how this HalfAdder logic design can be done in VHDL. So this is your VHDL. This is your VHDL. I mean the Xilinx ISC. It is integrated simulation environment. This is your project navigator. Now to start with, in ISC simulator integrated service simulation environment, where to start with you need to start with a project. So here you need to click file, then new project. Okay, I hope the prerequisite things you all know about the Xilinx software ISC simulator, and I am explaining the VHDL code only, not going to explain this the platform. Okay, later on in a separate video probably I will explain this wizard and entire detail of this software. So first you need to put a name for that. Okay, so I am just put it the project name as HalfAdder. Okay, HalfAdder. So location, it is showing C user HalfAdder, so later I will change it. So I'll put it in my app drive inside this, inside this, here I'll create one folder, same VHDL. Okay, in this folder. So now with this name HalfAdder, there will be a folder created within this. Okay, you can write some description. Okay, then you can write, this is optional, you can write the description about this. This is the HalfAdder program. Then the important is select the type of the top level source for this project. So if you see, there are primarily two types of top level source. One is VHDL and another one is Verilog. Okay, here we are going to do the HDL. There can be schematic, EDIF and SG or NGO, because this is primarily for the VLSI design. So we are not looking the software in that VLSI context, but rather we are using this for the digital design, or you can think of it as a first step of digital VLSI design, because first step of the digital VLSI design is the logic testing or logic simulation. So we'll use HDL. Just click next. Once you click the next, then this new project wizard comes, in which the project settings, because as a part of the VLSI design, as I mentioned, the first step of the VLSI design is for the logic testing, simulation and hardware testings. So that means once we simulate the logic here in the HDL, then next step is to test it in hardware. So while testing it in hardware, some generic hardwares like FPGA and the CPLDs are available, which you can interface with your computer, you interface with the software and dump the VHDL code into that generic hardware and can test it for the logic. But here we are not going to do that. We are going to only simulate the logic, so there is no significance of setting up this wizard. But still, I'll tell you about this. So property name hello. So Evaluation development board, what type of board you are going to use. As I mentioned, FPGA, CPLDs, different DSP boards, a lot many different boards are there. Then product category, different product category. Then family, device, particular device name. This is showing because it is none of the specified. Then package, different package, speed, top level source is the HDL already they have defined. Then synthesis tool here we are using Xilinx, so access the Xilinx synthesis tool. So once it is Xilinx synthesis tool, access the, it comes on with two VHDL. VHDL means VHSIC, V for very high speed integrated circuit, hardware description language, or it can be Verilog. So then simulator is ISIM. Preferred language can be Verilog or VHDL. Here we are going to do the actually there is nothing to specify here in this wizard, because we are not going to connect any hardware for this. Just I am explaining. Okay, these are the different things. So we are not going to do anything with this. Whatever be the specification specified here, let it be, because we are not going to use our hardware for this. Now just click next. Once you click next, it will show you the summary of the project. So project summary. Then as you see here, project navigator will create a new project with the following specification. These are the specification. Project name I have given HalfAdder. The path is this, in the F drive in this folder. Then working directory the same. Then description as I have written, this is the HalfAdder program. Then top level sources HDL, and this is the summary of the hardware specification that, as I have said, here is nothing to do with this. Okay, so if these things are correct, then you can put finished. Once it is finished, it is taking sometimes for the first time. Okay, so now see here in this design part, and this is your processing. So in this design part, it is showing HalfAdder, that this is the hardware actually, which, as I mentioned, there is nothing to do with this for the time being, but it is showing whatever be the specification was there at that time. Okay, now I would like to add a source file for the VHDL. So right click on it, new source. So then this wizard will open up. Okay, new wizard, source wizard. So select the source type, and this select source type, file name. Okay, now you see the schematic, user document, Verilog module, Verilog test spacer, VHDL, VHDL library, VHDL package, VHDL test bench, and some embedded processor. So here I would like to select VHDL module. So you need to put some name. Okay, so name of the VHDL module. But remember, whatever be the name you will give, this will be the name of the file, as well as this will be the name of your entity. As in a VHDL program, the first is the library declaration and second is the entity, and for entity you need to provide the name of the entity. So whatever be the file name you will give, that will be the name of the file, source file, as well as will be the name of the your entity. So I am just putting, say, since I have given the HalfAdder as the project name, so here I am putting just HA, capital HA. So file names are case sensitive, so capital HA, HalfAdder. So you see the location, it should be the same for that project, and it should ensure by default it will be checked, but still you ensure that it clicked, it checked add to the project. Add to the project means it will add this file in this HalfAdder project. Then click on the next. Once you click on the next, then this wizard will come up. This is the wizard where you need to specify the ports of the entity. Okay, ports of the entity, and you can put the name of the architecture, because in the VHDL program, the first is your library declaration, which in Xilinx or IRC tools it comes automatically. You need not to worry about that. You need not to write the code for that. Second is the entity declaration. After that entity, mainly in VHDL there are three types of modeling is possible. One is behavioral, one is structural, another one is data flow. So accordingly, if it is suppose behavioral, the next phase is the architecture body of the program. Okay, and finally finished. So these are the main component of the program, that is library, entity, and architecture. Now, as I have mentioned, you should have a name of the entity, and the name of the entity is by default the name of the file or source file. So you see here I have given the source file name as HA. You see that entity name showing here as HA. So after entity there is architecture, so you should have a name of the architecture. So architecture name also showing default behavior. You can change it. Okay, you can change it. It's just the name. Okay, let it be same behavior. Okay, now next you need to define the ports here. So a port is nothing but the inputs and the outputs. Now as you see in your HalfAdder, there are two inputs A and B, and there are two outputs sum and carry. So you need to define those ports here, input output. So say A is my input, just the direction in. If it is single bit, it's done only. If it is multiple bits, say 4-bit, 5-bit variable, then you need to click bus and need to provide MSB, LSB, most significant bit less than. But now for the time being, it is our single bit. Similarly, port B, this is also an then say output is sum. These are just like a variable. You can put any name. So this sum is my output. So you just click on it. Out. There are three types of direction is possible: in, out, in, out. In as an input, out as an output. In, out is something. Sometimes what happens? Output of the first is the input to the next. So in that case, if you would like to define, then it has to be in, out. So for the time being, it is just out only. Similarly, another one is carry. This is also out. So that's all. That entity being declared. So just click on the next. It will show you the summary. Okay, summary, whatever you have specified. If it is fine, then click finish. Once you click on this finished, you see that the VHDL program, you see this one here. So it is 3 squared box as a triangle means the top level source, where this HA is the name of the file, also the name of the entity. Behavioral is the name of the architecture, and you see HA.VHD, the extension is VHD. Okay, so this is the program comes automatically. Now in this program, whatever be the green part you have seen, green part is the comment. So that means comment is started with this double hyphen. Okay, so here it is showing something company, engineer. You can type company name. Here, so company I am typing ADBU, for example, engineer. Suppose I am putting my name. So create date and time, design name, say HalfAdder for, then model name, it is comes automatically. We have a project name, target device, tool versions, description, all or immediately these are just a comment. Okay, as I mentioned, the first part of the program is the library declaration. You see, you have not mentioned, you have not written any code for the library, but it comes automatically, which is a standard library followed by IEEE. Okay, so this whatever be the blue words you see, this blue are the keyword. Remember, keywords, which are like commands. Okay, code, syntax. So library is a keyword or a syntax. IEEE is the used library. So now this is generalized library IEEE, and out of which what part of the IEEE library you are using. For that, the command is or syntax is use. Anything blue you see is the keyword. So IEEE.std logic. Std means standard logic. 1164 was the version. .all. All means it will take for this program, it will take all the libraries included there in the IEEE. These are just some comment. You may delete it and comment the following library declaration of using, like that you can delete. Okay, so this part is only the library. Now if you'd like to have more some other libraries, you need to write here like this. For the time being, for this particular program, this is sufficient. Now next part, as I mentioned, is the entity declaration. So you see, this is your entity. declaration. Now for declaring the entity, again the syntax is entity. As I mentioned, the name of the entity will be the same as the name of the file name. So as I have given file name HA, so entity comes automatically as a. So these are the ports where I have defined is the coming automatically. So you see entity HA is also keyword. This is the syntax of the program, how we define the entity. Entity is the syntax, the name of the entity is a syntax. After that, port is a syntax. Here in the VHDL, remember one thing, here in the VHDL, the command or the syntax are case insensitive. That means capital title, small letters, all are same. Case insensitive. So port within first bracket, A I have defined it as in, since I am using the std logic, so it is comes std logic, B in std logic, sum out std logic, carry out std logic, end. So here you have declared the entity, here you are ending the entity, and every statement is being terminated by semicolon. It comes automatically, you need not to write, and this bracket is closed here. Okay, so this part is the entity, this part is the entity. After that, the architecture. As I mentioned, the second step is the second means third, actually this is library first, entity second, third is the architecture. So this architecture, as I have said, then there should be a name of the architecture, which is behavioral, comes automatically, you may change it. So for defining the architecture, the keyword or the syntax is architecture. So this behavioral is the name of the architecture. Of is again the keyword. Of what? Of the entity declared. So entity name HA. Now remember, this and this should be same, case sensitive, and is the keyword. Then this architecture begins here. So in that, after that begin, what you can do is you can have a process statement. So for the process statement, again the keyword is process. Okay, you see, once it is a keyword, it comes blue automatically. So process statement within bracket, what are the ports or things you are going to process? The inputs only, so A, comma B. So after that, the process has to be begin. So once process is being declared, then you have to begin that process. Again, begin, begin. Begin. So then the main part of the program, the syntax you need to write. So as you know, this sum is nothing but A XOR B, carry is nothing but your A and B. So the assignment operator here is, so sum, same, exactly the same variable you have to type this sum is assigned with, this means is assigned with, this is the syntax. Okay, is assigned with what? A and A XOR B. A XOR is a keyword, XOR B, semicolon. Then carry is nothing but A, and is also keyword A and B. Okay, since the processes begin here, so you have to end the process, that is nothing but end process. Okay, then the architecture was begin here, so you have to end the architecture, end behavior, it comes automatically. So that's all. So the program part is done. Okay, program part is done. So then you save the program. Once you save the program, these are the different process showing. The different process can be done. Okay, so first let me see whether there is any syntax error or not. Because as you know, program, whenever it is a software program, there is always two things, mainly syntax and semantics, and the compiler or the simulator, whatever the platform, will show you the syntax error, not the semantics error. So let us see whether there is any syntax error or not. So that you can see here in the under synthesis XST. So if you expand this synthesis XST, you can see here is check syntax. So double click on it, it will run for checking the syntax. So it is running. running sex index, and the consolation part is here. Here you can see the results. It is running. Sex syntax is running. So it checked green, that means there is no syntax error, or it is also showing here process sex syntax completed successfully, that means there is no syntax error. So program is error free, syntax error free. There may be semantics error. Semantics is the logic that you are implementing. Okay, next you need to simulate this logic for different in and out. Okay, that means to test the logic or truth table. So for that you need to have another source file, which is a test bench. So you just right click on it, then click on again new source. So you just type here the name again. Suppose I am typing HalfAdder underscore tbw. Tbw means test bench waveform. This is just the name. So now you see here different again source type. What type of source I need? Test bench. So VHDL test bench. This particular version of the ISC does not support the test bench waveform. So here you have to write the code for the test bench as well, VHDL code for the test bench as well. So I am just clicking on the VHDL test bench waveform, not the waveform, so VHDL test bench. Next, you should see whether it is associated with the same VHDL file or not. Yes. So next, it is the summary, then finish. It will show you another program, which is also a .vhdl program for the test bench. You see, this is the VHDL program for the test bench. Here also you need not to do much things. Almost main major things already been come automatically. Here also entity comes automatically. Library comes automatically. Then entity, architecture, ports are being defined. As a component, the structure showing as a structural program. Signal A and B, because these are the two of my input. Sum and carry as my output. There is it's showing a constant clock, but I am not going to use any system clock, so there is no need of this part. So what you can do is you can make it command. We need not to have this clock, because in sequential circuit we need to have a system clock, but here in the combinational I will not going to use this system clock. Next, initiation, these things. Then clock process identified. This part also not required, because I have not going to use this, so therefore this clock process initiation also not required. I'll just put it as a comment. So I don't need. Then simulation process. So simulation process, this is the name of the process, steam process. Begin. Now whole reset state for her, so it is showing the time, so it will wait for the 100 nanosecond. Then wait for the clock period, but I am not going to use this clock, so I can delete it or make it comment. So say A is not A, because just I need 1010 kind of thing, so not A. Okay, so I am putting it as steam process 1. Sorry, steam process 1. Then wait, or I'll put it as wait for say 200 nanosecond. Okay, end process. Similarly, I need to have another process for B. So now I'll make it as steam process 2. Then wait for say 150, just to have different timing, 150 nanosecond. This is up to you how you are managing with the time. So not B, then here I am giving say 250 nanosecond in process N. So that's all. Just save it. Then while you click on the simulation, that file will be showing this is a in the simulation, not in the implementation. So you just click on it. Here you click. Then you can seq syntax this program, behavioral seq syntax. So completed successfully means there is no syntax error in this program. So that's all. The test bench is created. Then I am going to simulate it. So what to simulate? This test bench. So you just double click on this simulate behavioral model. Once you double click on this simulate behavioral model, so it is showing, you see, this is the your test bench waveform. So I'm just clicking on this. It is showing the different timing as per the timing given, or you may change it according to your choice. Okay, so by this line you can see whether it is following your truth table or not. Suppose at this point it is showing the value A is 1, B is 1, so sum is 0, carry is 1. Similarly, suppose I am moving it to here, 0, A is 0, B is 1, sum is 1, carry is 0, correct. Suppose here I am showing A is 1, B is 0, sum is 1, carry is 0. That means it is following the truth table, A 0, B 0, sum 0, carry 0. So that means it is correct, 1, 1, 0, 1. Okay, so this timing waveform you can change it. You can change it. You can expand it, zoom it. You can zoom it. It's up to you. Okay, or you can change the timing as well. So that means it is correct. So let's just save it, or you may close it. Okay, I don't want to save it for future. Okay, just close it. Close means only this you need to close. Okay, no. Or yes, let it. No. Okay. Then come to this again. Let it close completely. Okay. So that means logic is simulated correctly. Now let us see the circuit, TTL circuit. So we go to the implementation again. You see, you click on this, it is already clicked. Then view RTL schematic. There are two for the synthesis. There are lot many options. Here we will not go to the other options. Our objective is to just simulate the logic, then test the circuit. So logic simulation is done. Then I'll see the schematic of the RTL or register transistor logic. That is also falls under that something TTL. So synthesize, access the synthesize Xilinx simulation tool under which view RTL schematic. Double click on it. Once you double click on it, new window will open up for the RTL schematic. Okay, now select how RTL is to be viewed. Start with the Explorer user, start with the schematic with the top level block. It's up to you. So let it be start with the schematic of the top level block. Okay. So new window is opening. This is the box. The block that we are going to design. That means this one. Okay, then if you double click inside this, you will see the circuit. This is the circuit. So let it zoom in. Okay, so this is your AND gate. A comes here, B comes here, and this is your XOR gate. In VHDL, this XOR gate is not showing directly. In VHDL, it is always follows the AOI logic, so enter inverter. So XOR is nothing but A bar B or A B bar. So if you double click on it, you'll see that. Just close it. I'll write it again. Virtual schematic, we'll see. Start with the Explorer. Okay. So which one you see? HalfAdder primitive. So carry I'd like to see. Create schematic. This is carry A and B. Then sum. This is the sum. Or remove it. Only sum I would like to see. This is only sum. A XOR B. Then if there is any signal, suppose A, A is showing where A is going. Then similarly B. This is your B. Okay. Then top level ports A, B. So I'm just removing this. And then this top level source will see together. So it's A, B, sample. Okay. Or directly primitive, query sum. Just complex. Okay. Also, you can see the technological schematic. Double click on it. Again, these two things. Okay, start with the top level block. Okay, so this is again the same thing. Inside which you can see the technological schematic. So this is the A XOR B part. This is A and B part. This is this A XOR B part. This is A bar B, A B bar, and this is your A B. Okay, you will get in technological schematic, you will get these buffers. Don't worry, because while giving any input, it should actual technologically it should throw buffer. That is what is buffers are showing, input and output. So if you double click on it, you see this AND gate. You will get the equation for this A and B. You will get the truth table for this Karnaugh map A B only. Similarly, if you look at this is A XOR B. Equation this A, this is showing like technologically, not A and B or A and not B. It is showing the XOR truth table. Karnaugh map, if you see these two, so there is A bar B, sorry, these two, green one, A bar B, A B bar. Okay. So this is your what we do with the VHDL. It's done. It's done. This is your multisim. You can check that same. So here also lot many other things you can do. I am just showing you only the only the simulation part. Okay, so this HalfAdder part is done. Now what is the problem with this HalfAdder? First of all, it is only single bit. For example, I am going to add up a 4-bit number using this my HalfAdder. So A3, A2, A1, A0 is my first 4-bit number for A. B3, B2, B1, B0 is my second 4-bit number to be added as B. Now what happens if I would like to add up these two numbers using this HalfAdder? What to do? First I have to apply A0 here, B0 here. Okay, so when A0 here, B0 here, two results will come, sum and carry. So sum I am considering as not, carry I am considering C not. So as per the normal addition, where C not will go? C not will go to the next column here. So in the next column, C not, A1, B1. So what you have to do here, since it offers only two inputs, so you can apply only two at a time. So C not, A1, here you have to apply C not, then A1. Then again see the results, along with the results you have to again put B1. Okay, so that becomes a lengthy procedure. That is the disadvantage of the HalfAdder, because that is it has only two input. Okay, so that can be overcome by using FullAdder. So in FullAdder there are 3 inputs. Okay, so please follow the consecutive lectures. In the second lecture I'll cover up the FullAdder in both Multisim and VHDL. Okay, thank you very much for listening.